Sunspot region AR4436 has spent the last 11 days firing more flares at this planet than any other active region on the solar disk. And as of this morning, May 21st, 2026, it has rotated past the northwestern limb of the Sun, taking its most prolific flare production to the far side, while its accumulated legacy of coronal mass ejections, radio blackouts, and ionospheric disruption has left NOAA's Space Weather Prediction Center in a state of sustained operational alertness. The region is gone from direct view. But the question that every space weather physicist is asking right now is not what it did when we could see it. The question is what it is doing on the side we cannot. If you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources. USGS, NOAA, the Smithsonian Global Volcanism Program, NASA, and peer-reviewed research. But official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed. The data is public. The responsibility to check belongs to all of us. But that is not even the complete picture. What the headline describes as a sunspot is not a blemish on the surface of the Sun. It is a region of magnetic field so intensely tangled, so violently concentrated, that the solar plasma above it is suppressed, cooled relative to its surroundings by thousands of degrees, and what emerges from that suppression, when the magnetic field lines finally snap and reconnect, is not heat and light in any ordinary sense. It is a detonation, a release of energy equivalent to billions of atomic bombs, compressed into a matter of minutes, launched outward across 150 million kilometers of space, arriving at the only planet in this solar system known to carry a living civilization, arriving at its power grids, its satellites, its communication infrastructure, its hospital systems, its water treatment plants, its financial networks, arriving, in other words, not at an abstract technological system, but at the precise machinery upon which 8 billion human lives now depend, moment to moment, without pause. AR4436 is not a hypothetical. It is a documented region. NOAA's Space Weather Prediction Center assigned it that number, tracked it, measured it, issued operational alerts about it. On May 10th, 2026, 11 days before today, at exactly 13:39 Universal Time, it erupted with an M5, 7-class solar flare. M-class flares are the second highest category on the solar flare classification scale, and an M5, 7 is near the top of that tier. Within minutes of that eruption, high-frequency radio communications across the entire Atlantic Ocean were knocked offline. Ships in transit, commercial aviation, amateur radio operators, military communications, all of them experienced the same thing simultaneously. The signal disappeared. It did not fade, it did not degrade, it was there and then it was not. Because what travels at the speed of light from the Sun does not give warning. The X-ray radiation from that flare reached Earth's upper atmosphere in approximately 8 minutes, and it ionized the ionosphere, the layer of charged particles that bounces radio signals around the curve of the Earth, so intensely that those signals had nowhere left to bounce. They fell into the ionosphere and vanished. That was the first wave. The second wave was slower, and in some ways more consequential. The M5. 7 flare also launched a coronal mass ejection, a CME, which is a fundamentally different kind of event. Where the X-ray radiation travels at the speed of light, a coronal mass ejection is a physical eruption of magnetized plasma, billions of tons of solar material flung outward through the inner solar system. That CME, launched from AR4436 on May 10th, took 3 days to cross the 150 million kilometer distance to Earth. NOAA forecasters and the UK Met Office both modeled its trajectory and determined that the bulk of the material would travel on a path passing just behind Earth's orbital position, a glancing blow rather than a direct hit. The outer edge of that expanding plume reached Earth approximately on May 13th, delivering a minor G1-class geomagnetic storm. G1 is the lowest category on the 5-level geomagnetic storm scale. It was not the worst-case scenario. But here is what the data also shows. AR4436, even as it generated that CME, was still rotating into what solar physicists call the strike zone, the region of the Sun's Earth-facing disk, where any ejection launched will travel in a direction that puts Earth squarely in its path. As the region rotated further into that zone over the following days, it continued producing flares. It continued accumulating energy. And now, as of May 21st, 2026, it has rotated out of direct view, not because it has quieted, but because the Sun itself has turned, carrying that region around to the far side. What AR4436 is doing on the far side of the Sun right now cannot be directly observed from Earth. What is known is that it has not simply stopped. And here is where this account becomes genuinely significant. The coronal hole that is currently facing Earth on May 21st, 2026, a separate solar feature, a gap in the sun's magnetic field through which the solar wind flows freely and at elevated speed, is now the dominant geomagnetic influence on Earth's environment today. NOAA forecasters have predicted quiet to unsettled conditions for May 21st, with solar wind from that coronal hole providing active enhancements, quiet to unsettled. That language is precise, and scientists choose their language carefully here. And that careful language is itself the warning, because unsettled conditions, in the context of a sun that is currently at or near its solar maximum, the peak of its 11-year activity cycle, the moment when its magnetic poles are in the process of flipping, when flare production reaches its highest rates and its most intense outputs. Unsettled conditions on any given day do not tell you what tomorrow's conditions will be. The solar maximum is not a single moment. It is a sustained period of elevated activity that can last months or years. And the monitoring community has been clear. The sun is in that period now. The active regions on the far side of the solar disk are being tracked by instruments that measure the reverberations of solar activity through the body of the sun itself, a technique called helioseismology, which detects the signatures of sunspot regions the way a seismograph detects the movement of rock far beneath the surface. Those instruments are showing strong active region signatures on the far hemisphere. Their arrival on the Earth-facing disk, when the sun's rotation brings them back into the strike zone, is not a question of whether. It is a question of when. And when AR4436 reemerges on the other side of that rotation, in approximately 2 weeks, the question of what it has been doing while we could not watch it will have its answer. To understand why any of this matters, it is necessary to go back, not to last week and not to last year, but to the morning of September 1st, 1859. On that morning, a British amateur astronomer named Richard Carrington was in his private observatory, doing what he did most mornings, sketching sunspots through his telescope, methodically recording the position and shape of the dark regions on the solar disk. At 11:18 in the morning, he observed something that no astronomer had ever recorded. 2 brilliant patches of white light appeared on the surface of the sun, near a large and complex sunspot group. They were so intense, so unexpected, that Carrington immediately called for a witness. By the time the witness arrived, the white patches had already begun to fade. Carrington checked his clock. The entire event had lasted approximately 5 minutes. What he had seen was a solar flare, the most powerful one in recorded history, and what that flare launched toward Earth was a coronal mass ejection that would take only 17.5 hours to cross the distance from the Sun to Earth. That transit time is deeply significant. A typical CME takes 2 to 3 days, the 1859 CME took 17.5 hours. That velocity tells you something about the magnitude of energy behind it. When that CME struck Earth's magnetosphere on the night of September 1st and into September 2nd, it triggered the most intense geomagnetic storm ever recorded in human history. The storm is now known as the Carrington Event. Auroras blazed across the sky, not just at high latitudes, but across the Caribbean, across Central America, across the southern United States. Auroras so bright that gold miners in the Rocky Mountains woke up, saw the light, and thought it was dawn, then realized it was 2 o'clock in the morning. In Boston, people read their newspapers by the light of the aurora. In the southern hemisphere, the southern lights were seen as far north as Queensland, Australia. The entire planet was bathed in electromagnetic fire. The telegraph system was the critical infrastructure of 1859, the internet, the banking system, the emergency communications network, all compressed into a single technology. And the Carrington Event ran current through those telegraph lines so powerfully that operators across North America and Europe reported receiving electric shocks from their equipment. Some of them disconnected the batteries that powered their machines and found, to their astonishment, that the lines continued to work not on battery power, not on any human-generated source of electricity, but on the geomagnetic current induced by the solar storm itself. The sun was operating the telegraph system. The sun was, for those hours, the power company for the entire planet's communication network, and when it decided to stop, telegraph stations caught fire. This is not a hypothesis. This is documented in the geological record and in the newspaper records and engineering logs of 1859. Ice core samples drilled from Greenland and Antarctica have preserved the chemical signature of the Carrington Event in layers of ice laid down 167 years ago. The nitrate deposits produced by the intense particle bombardment of Earth's atmosphere are still readable today. Those same ice cores reveal that the Carrington Event was approximately twice as large as any other solar storm of the last 500 years. Twice, the second largest event in half a millennium, and it hit a civilization whose most sophisticated electrical system was a wire and a battery. Now consider what the civilization of May 21, 2026 has built on top of those wires. The electrical grid of the United States alone carries power to approximately 330 million people across a network of roughly 450,000 miles of high-voltage transmission lines, connected to an estimated 2,000 extra high-voltage transformers. Those transformers are the single most critical vulnerability in the entire system. They are enormous, custom-built pieces of equipment, each weighing up to 400 metric tons. That is the weight of more than 60 adult African elephants. If you need a scale your body can hold, and they take between 1 and 3 years to manufacture and deliver. The United States currently holds a limited strategic reserve of spare transformers. The reserve is not adequate to replace multiple simultaneous failures across multiple grid regions. A 2013 joint risk assessment published by Lloyd's of London and the research firm Atmospheric and Environmental Research modeled what a Carrington-level geomagnetic storm would do to the North American grid. The headline number from that report is an economic cost estimate of between $600 billion and $6 trillion US. The upper bound scenario involves between 20 and 40 million Americans losing electrical power for durations ranging from 16 days at the low end to 1 to 2 years at the high end, 1 to 2 years without electricity. Not a blackout that lasts a weekend. Not a storm that knocks out the power for a week. 1 to 2 years in which every hospital, every water treatment facility, every refrigerated food supply, every heating and cooling system, every financial transaction, every internet connection, every mobile network, all of it runs on backup generators until the generators run out of fuel and then it stops. Consider the 622,000 people who live in Milwaukee, Wisconsin, a city that sits at altitude, making it significantly more vulnerable to geomagnetically induced currents than cities further south, or the 7 million people in the metropolitan area of Chicago, Illinois, whose grid is fed by transformers that have been identified in academic literature as being among the most exposed to geomagnetic storm effects in the United States. Ask what those people, the nurse beginning a 12-hour shift at Northwestern Memorial Hospital, the logistics coordinator managing refrigerated medication shipments at O'Hare International Airport, the family in a third-floor apartment whose tap water depends on electric pumps to reach them, ask what those people would do in the first 48 hours after power disappeared from a grid that had no timeline for restoration. Not because this is a speculation exercise, because the data that describes that scenario is drawn directly from peer-reviewed engineering assessments and official governmental risk models. The question those people would ask if they had access to the data in front of you right now is not a rhetorical question. It is, why did no one tell us? The answer, to the extent there is one, involves the gap between what the science knows and what public policy has implemented. Scientists at NOAA's Space Weather Prediction Center can now detect a solar flare within seconds of its eruption, analyze the CME trajectory, and issue geomagnetic storm watches with lead times of 1 to 3 days. 1 to 3 days, that is not nothing. That is enough time, in principle, for grid operators to reduce electrical loads on the most vulnerable high-voltage lines, for satellites to enter protective safe modes, for GPS-dependent systems to activate backup navigation protocols. The monitoring infrastructure exists. The warning capability exists. What the Center for Astrophysics at Harvard and the Smithsonian has now produced after 18 years of field measurements at more than 1,800 locations across North America is a three-dimensional map of the electrical properties beneath the continent, tracing exactly how geomagnetically induced currents would flow through underground rocks, ancient geological formations, and the conductive pathways of the Earth's own crust during a major storm. That map reveals that certain regions, particularly those underlain by highly resistive ancient rock, force geomagnetic currents up into the power grid above them rather than dissipating them safely through the ground. The eastern United States is particularly vulnerable for this reason. The geology itself amplifies the risk. But the monitoring and the mapping are only as useful as the protective hardware that acts on their warnings. A 2008 report from the National Academy of Sciences identified the installation of blocking capacitors on the most vulnerable transformers devices that would prevent geomagnetically induced direct current from entering and overheating those transformers as a technically feasible and relatively affordable hardening measure. The cost of fitting blocking capacitors to the approximately 1,000 most vulnerable transformers in the United States was estimated in that period at roughly $100 million, against an upper bound loss estimate of $6 trillion, against the possibility of 20 to 40 million Americans without power for up to 2 years, against the geopolitical, humanitarian, and industrial consequences of a civilization whose electrical infrastructure has been burned out by a star that has been doing this for 6 billion years and will continue doing it long after the last human being has made the last decision about whether or not to spend the money. After the 1989 Quebec blackout, which was itself a far smaller event than the Carrington Event, produced by a geomagnetic storm that was significantly less intense, and which nevertheless knocked out electricity to 6 million people in northeastern Canada for 9 hours, collapsing 21 gigawatts of supply in the space of less than 1 minute after that event, the Canadian government invested approximately $2 billion Canadian dollars in hardening the hydro grid. That investment was made because the evidence existed, the data was clear, and the decision-makers of that moment chose to act on it. The question of whether similar decisions will be made at a scale equal to the actual risk before our 4436 or its successor completes its next rotation into the strike zone is not one this script can answer. The data can describe the risk. It cannot compel the response, and the risk is not limited to the electrical grid. A major geomagnetic storm disrupts GPS satellite signals, which are used not just for navigation but for the synchronization of financial trading systems, the timing of cellular network transmissions, and the coordination of air traffic control. It degrades satellite communications. It accelerates orbital decay for low Earth orbit satellites by heating and expanding the upper atmosphere, increasing drag, and causing spacecraft to re-enter earlier than planned. It irradiates astronauts in orbit. It disrupts the pipelines that carry oil and gas across continents because those pipelines accumulate geomagnetically induced current the way a wire does, and when enough current accumulates, it accelerates corrosion from the inside. A study published in peer-reviewed literature estimated that a Carrington-level event could add years of equivalent corrosion to exposed pipeline infrastructure in a matter of days. The system is not composed of isolated components. Every piece of modern infrastructure is connected to every other piece through the electromagnetic environment in which they all operate, and that electromagnetic environment is defined, ultimately, by a star 150 million kilometers away that does not consult human schedules, what the sun is doing on this particular morning. May 21, 2026 is, according to NOAA, quiet to unsettled. Our 4436 is over the limb, out of direct view. The 5 numbered active regions remaining on the Earth-facing disk carry simple magnetic configurations, with low risk of strong flares from those currently visible regions. The coronal hole stream is providing mild active enhancements. No significant geomagnetic drivers are currently in play. This is, by any short-term measure, not a crisis day. It is a background-level day in a period of elevated solar activity near the peak of a solar maximum cycle, with a historically productive active region temporarily on the far side of the sun, and a scientific community maintaining what NOAA officially describes as heightened monitoring protocols. Heightened monitoring, the system is not inactive. It is accumulating. What accumulates in periods of solar maximum is not just flare energy in active regions on the sun's surface. It is also the statistical probability that, across the months and years of peak activity, one of those active regions will produce an event at the upper end of what solar physics considers possible. The Carrington Event of 1859 was that upper end, the near miss of July 23, 2012, when a Carrington-class coronal mass ejection was launched by the Sun and crossed the exact orbital path of the Earth. 9 days after the Earth had moved past that point demonstrated that events of that magnitude are not once in recorded history occurrences. They are recurrent features of an active star's behavior. NASA scientists who studied the 2012 event estimated that if it had launched 9 days earlier, it would have struck Earth directly. The estimated damage to the United States alone, up to $2 trillion. The estimated recovery time for the electrical grid, years. Think about the city of Karachi, Pakistan, home to more than 16 million people, one of the most densely populated urban centers in the world, situated in a region where the electrical grid is already strained, where backup generation capacity is limited, where the supply chains for major transformer components require months of international shipping. Think about what those 16 million people, the shopkeeper opening at dawn, the doctor arriving for morning rounds at the civil hospital, the mother whose young child depends on a powered medical device, think about what those 16 million people would experience in the hours and days following a grid failure with no projected restoration timeline, not because this is unique to Karachi. Because it is true in Lagos and Cairo and Jakarta and dozens of other megacities where the population density exceeds the grid's resilience margin and where spare transformer inventories exist in the single digits, the human face of this risk is not a concept. It is a morning routine that depends on electricity, in a building that depends on pumped water, in a city that depends on refrigerated food, in a civilization that has built every layer of its survival on a technological infrastructure that was designed without a full accounting for what the sun can do. The question is not whether the sun will produce another major geomagnetic storm. The question is not whether our infrastructure is vulnerable. The question is not even whether the monitoring capability that exists could provide enough warning to take meaningful protective action. The answer to all 3 of those questions is already in the scientific record, and it is yes, yes, and conditionally yes. The question that remains open, the question that the data cannot resolve, is whether the gap between what the science knows and what the infrastructure can withstand will be closed before or after the next major event arrives, and that question has no answer in this script because it has no answer in the data. It belongs to a category of human decision that is made not in observatories or research centers, but in legislative chambers and boardrooms and procurement offices, by people who have, in many cases, not yet read the reports that exist. Our 4436 fired its most powerful flare of the current observation period on May 10, 2026, at 13:39 Universal Time. It disrupted radio communications across an entire ocean basin. It launched a coronal mass ejection that glanced Earth 3 days later. It continued producing flares through May 19th, firing 7 of the 8 recorded flare events on that day alone, before rotating past the limb and out of direct observation on the days immediately preceding today. In 11 days of visibility, it rewrote the space weather forecast multiple times and kept 5 separate national and international monitoring agencies in a state of continuous operational alert. That is the record of a single sunspot region during a single rotation of the sun. The sun completes one rotation approximately every 27 days as observed from Earth. In the 11 days that our 4436 was in direct view, it behaved exactly as the solar physics literature predicts active regions near solar maximum are capable of behaving. It was not an anomaly, it was a demonstration. What the demonstration shows is a system that is operating precisely within the parameters that make it dangerous to the civilization built beneath it. The sun is at solar maximum. Active regions are proliferating. The monitoring is in place and detection is possible, but prediction is not at the level of precision that would tell a grid operator on the morning of May 21, 2026, whether the next major event will arrive in 3 days or 3 weeks or 3 months. That uncertainty is not a Failure of science. It is an honest description of the current state of solar physics, stated plainly by the scientists who do that work. The instruments are extraordinary. The physics is well documented, and the gap between what can be detected and what can be predicted with operational precision remains, as of this morning, unbridged. On September 2, 1859, the morning after the Carrington Event peaked and began to subside, telegraph operators across the United States and Europe went back to work on lines that were still warm from the night's electromagnetic bombardment. They filed their reports. They noted the disruptions. They continued operating because the infrastructure they depended on, fragile as it was, simple as it was, had survived more or less because it was simple. There were no transformers to burn out, there were no semiconductor chips to fry, there were no satellites to lose, there were no hospital ventilators running on grid power. There were no water treatment plants dependent on electric pumps. There were no financial clearing systems whose timing signals came from a GPS satellite. The telegraph was damaged. It was also, in a matter of days, operational again. The infrastructure of May 21, 2026 is not the telegraph. It is something orders of magnitude more complex, more interdependent, and more difficult to restore once disrupted at scale. And the star that produced the Carrington Event 167 years ago is the same star in the same phase of a cycle it has been completing for billions of years that produced the M5. 7 flare from R4436 on May 10, 2026, and that is currently rotating an unknown collection of active regions on its far hemisphere toward the Earth-facing disk, where they will emerge, in approximately 2 weeks, into the strike zone once again. The sun does not know that we are watching. It does not know that we have built our civilization in a way that makes us vulnerable to what it does routinely, on its own schedule, according to its own physics, without reference to our readiness. It has been doing this for 4.5 billion years. The most powerful geomagnetic storm in human recorded history took 5 minutes to initiate and 17.5 hours to arrive. The next one will not announce itself differently.